Hello, I'm Tyler, and I'm with the team that put together this shape detection and counting circuit. And we are excited to show you how every component works, how they work together, and how they produce the final result. First up, the scanner. Here's how we build the scanner. You'll see in my Vision C, I have input playing, and that will be the source from which we scan. Here, inside the main circuit, inside the scanner, we have the first big region called the vision sampler. This is where we're going to put the video feed from Vision C that we actually want to be sampling. Essentially, when the scanner is actually working, you will see a moving subset of the Vision C feed inside Vision Sampler. In order to make that actually happen, we first need to have the sweeper. Down here, way at the bottom, we have two areas, an input area called the start scanner and the 4x4 scanner. The start scanner, all it is a 1x1x1 area that we will make start the 4x4 scanner. So right now it's fully working, but it isn't currently scanning. That's because we haven't supplied the initial potential necessary in order to get the process going. And in order to do that, in a moment, once I explain 4x4 scanner, we will select manually the neuron in the start scanner via just a shift click and then hit space to manually fire it. Now, as you can see, we are seeing a shifting, scanning feature take place. It is gradually scanning over its own local area, and that local area is then projected onto the larger sampler that we just now looked at. Now, how is this happening? Very simple. First, we have a projector connection going directly into scanner, which just applies uh, a bit of potential to actually get things started with the first little neuron. But on the 4x4 scanner, the real power comes from a handful of recursive connections. First, we have the sweeper. This is a built-in feature of FEAGI that takes care of the sweeping motion that's actually taking place over the full cortical area. We also have last to first. That is the area that is ensuring that our sweep actually restarts. If you want to use this in a different situation, you can simply delete this connection and it'll just run through the whole scan one time instead of repeating over and over and over again. For testing purposes, we'll just leave it on. Then we have block to block, ensuring that potential actually stays inside the scanner, that we aren't actually losing it when uh, we stop manually firing that first neuron to get the process started. Then we also have inhibit prior. This is good for ensuring that we don't have too many repeated scanners at the same time, because we want a gliding box to move over the entire surface, a single box going from area to area to area. If we see multiple boxes at the same time, that will mess around with our final count, which we will see in a moment. Next up, we see, well, first, as you can see, we are seeing the circles gradually show up as the scanner actually progresses across the entire screen. This is done by turning down the power. Well, first, the Vision C is projecting directly into our vision sampler. And because the reason why it isn't firing all the circles at once is that we have a firing threshold set on the vision sampler that will only be crossed when the potential from the scanner is added onto the potential from the Vision C. And the end result is we see only one circle at a time as it gradually guides across the whole input. And as we can see in this last, most important area, which we use as the output so that we can send this image that we're creating into other areas for processing, is a 32 by 32 by 1 area that uses the tiler, again, a core connectivity rule within FEAGI, that takes whatever's firing all inside the vision sampler and crushes it into this size. And because we only have one area firing at a time, we just see one circle in this area at a time, ready for processing. Downstream from the scanner, we have the edge extractor. Now, in our particular situation, the files that we're scanning will usually have shapes that are bold, as in when they fire in Vision C, they come up pretty much completely filled with potential, like you see here. Now, this isn't inherently a bad thing, but what we really need to discern a shape is really just the edges. Uh, and when it comes to later pathways in the pipeline, all this extra firing potential will likely just get the system confused and hurt our ability to actually cleanly detect, which is why we put together this edge extractor, which utilizes a vector connectivity rule in between these two connections that effectively says whenever we get input directly from scanner's output, we will look over it, and any and all neurons that are surrounded by other firing neurons don't fire, don't get passed on. And that is the result that you're currently seeing in between the edge detector input and output, which is then passed on to the next phase of discussion, the angle detector and curve detector. Now, both of these areas are very similar. They involve a lot of the same logic, but we will go over simply the angle detection and show you the in-depth interpretation and implementation.
Hello, my name is Ryan Farah. Today I will be doing a walkthrough of the angle detection section of the circuit. As Tyler had mentioned previously, his image scanning section sequences through the image that is then sent to the edge extractor, of which the output is then sent into my angle detection. So let's have a look here at what's actually taking place. So firstly, this is the, make this a little bit bigger. This is the input for the angle detection. So this is where the main data stream comes in. And then it's sent to this rotational circuit where it is then rotated across various different degrees. This is very beneficial as this helps us detect angles at different rotations. So we could be able to detect different shapes at different rotations. From here, of these that are split up, they're split up into 4 main sections, which then have their core components broken down. So as you can see here, this is a vertical circuit, and the connectivity rule of this is such that it only flags vertical lines. So as you can see, anything that matches this connectivity rule of a straight vertical line would fire. So it will find that in the image that it's seeing, in correspondence with the horizontal line detector, finding horizontal lines, and together they are combined, and if there's any overlapping information, in the case of what would occur in a right angle, then the right angle cortical center would fire. So the basic logic is you break an image up into its base components, aka lines at different angles. So I've just shown you the vertical connectivity rule. Let's have a look at the top left to bottom right. As you can see, this is a vertical line, and we test for this subcomponent here. And then, vertical lines are used to determine if the angle is obtuse, acute, if 2 vertical lines are coming together to create the connection. And basically, from this data, we would be able to identify what angles are present in at what rotational offset. So here, at z equals -4, there is 0 rotational offset. So this is essentially the base image. So anytime the square fires, you can see that the vertical line is firing where the square is present, as well as the horizontal line. And because of this, the right angle norm is firing when the diagonal is not. So this is accurately detecting that there is a square present, or I should just say a right angle present. So the combination of these basic lines, so the right angle detection, the combination of vertical and horizontal, the two diagonal, which checks two diagonal lines, as well as two other combinations of these. Out of these four, only the right angle circuit is firing, which makes sense because at this rotation, it is just a plain square. So then this data is sent to the output at this rotation, which is then combined into the final output, which is then sent to our shape detection circuit, which is right here. So I'll save you guys the time, but the logic that I just explained for this one rotation occurs at various other rotations as well here. And as you can see, it's working somewhat well. So then later down the line, through training, of course, this circuit should be able to reliably detect the different angles present in an image.
Next up down the pipeline is shape detection. This particular area is very, very simple. So it takes input from angle detection's output and curve detection's output, as you see here. All that we're really looking for here is that some potential is passing through the angle detection and curve detection filters. Well, as you can see right here, this nice clean circle that we're getting as input has been absolutely destroyed in these cases. This is due to the filtering process that angle detection and curve detection are currently taking in effect. And we don't really care about that. It's perfectly fine. All we need is some potential to pass through, be reasonably certain that there is angles in our input and curves in our input. And when we have those factors together, we have a reasonable idea that we have a shape in our input. And so all that shape detection in this situation is doing is accepting these 32 by 32 by 1 areas and projecting uh, them and their potential into these little 1 by 1 by 1 areas. And these 1 by 1 by 1 areas then act as outputs for the input of the next counting circuit. Now, why 1 by 1 by 1? Well, it solely exists as the trigger for this shaped detect area. Like I said, this is the trigger that tells the counter, hey, we found a shape, increment the count by 1. Now, in order to implement the true count, the idea we have is to use these very long z-axis registers or cortical areas, as we have them here. And we choose to interpret the number of z-axis neurons, or the number of the z-axis neuron that is firing to be the count. Now, how do we accomplish that? Not quite as simply as the last area. In this case, we have these two 1 by 1 by 10 areas. And this first one, the shape register, as we can see right here, gradually fills up with potential as that earlier trigger. Now we're using recursive connections here and MP accumulation to bring this into effect, see the block for details, or see the actual circuit. In this case, when we first started the program, all of this lit up potential wasn't here. No neurons were firing. It was completely dark. But once we turned it on, that first signal that triggered the input neuron is way back neuron fire. Then when our trigger neuron fired again, so too did the second, then the third, then the fourth. Eventually, what we have now is a bunch of activated potential. Now, this is because our system has been running for a little while as we are doing this demo. But in a real world situation, you would see this very easily, especially once the last to first connection in the scanner is actually turned off. Now, having all these neurons fire, you and I can guess that the count has a meaning there, but we want to pass this on to the uh, thought detector's counting capabilities. In order for that to work, we need to have only one neuron firing, and the count of that neuron is the count of how many shapes we detected. So, you see the shapes in the shape count cortical area. The 10th, or z equals 9 neuron, is currently firing. And that is because this neuron, z equals 9, neuron number 10, the shape register, is. We are using a projector and a previous inhibitor to stop all previous neurons from firing. This way, we only get z equals 9, or neuron 10, to actually fire. And then we do a project this area into the count output area. As you can see, it's currently reading a count of 10. And if we opened up FEAGI, we could also see a count of 10 there. That marks the end of our circuit. We hope you enjoyed watching this video and are feeling inspired to try out FEAGI, join the community, and build something new today. Thank you for watching.